Thanks for the introduction. So I'm Ludovic Perret, so I'm professor at EPITA, and I'm specialist not of a doctor block. This session will be divided in two talks. So my talk will be kind of more high level, and it will speak about the impact of quantum to cybersecurity in general, and in particular to the case of blockchain, because as Max mentioned, there is a lot of cryptography involved there. So what I will try to explain you is what are the actual impact in my talk. And so in the next talk, you will see that how we can mitigate the risk by some practical implementation, and also the challenge which are related to the integration of a new type of cryptography. So from a high-level point of view, where is the cryptography involved and where is the risk related to quantum? So if we focus on the crypto part, from my point of view, and I guess you will be agree, so you have mainly two things that you have to take care. So the first one is related to the crypto puzzle, the proof of work, or the consensus mechanism, which will involve a hash function. So the first issue to consider is what is the impact of quantum related to the classical art problems that we have to consider on hash function. And so the second aspect is related to public key cryptography, and more specifically to signature algorithm, and in particular in XRPL Ripple. So we know that, and you will see that in the next talks, that you have elliptic curve-based signature algorithm which are implemented to authorize various type of contract or other type of things. Okay, so that's the overview. So we know in the classical setting that these building blocks are secure. So in the sense that we know perfectly what is the level of security of elliptic curve or hash function in the classical setting. So what is the impact of quantum on these building blocks? As a first disclaimer, you have to realize that a quantum computer is not just a magic computer that will solve any problem faster than what we have in practice. It can solve actually a very specific set of problems faster or much faster than in the classical setting. And even when we say that, we have to be careful about what is the status of the risk and what computer can really do, let's say, in the next 15 years. And for the two primitives that I mentioned, we have basically two algorithms to consider. So the first one is due to Grover. And so in the general setting, it says that given a function which give you an input of size n and give you 0 or 1, you want to recover a preimage of that of 1. So you can use Grover algorithm typically to do an exhaustive search, and you know that for this task to recover some preimage of a hash function, typically you know that the cost of exhaustive search, trying to find all these elements, is 2 to the n. And so that we know in the quantum settings that you can do this task quadratically faster. So this is about inversion of a hash function or second preimage. So a second task which is related to the hardness of hash function is collision finding. And so we know that if the output is of size n, classically it's 2 to the n over 2. And actually you do have a quantum algorithm which use Grover algorithm, which can do slightly better, 2 to the n over 3. So actually, with the technology that we have for quantum computers, until now, it is not completely clear that typically this algorithm, due to Brassard, Euler, and TAP, will be actually really more efficient than what we have today. And so this is due to that you have to store a large amount of data, and memory is quite costly. And so there is some discussion in the community to say, well, in fact, you have not this speed up actually with the technology that we have currently, let's say in the next 15 years. But anyway, I would say it's better to be more safe and to take into consideration these attacks, even if it can consider it to be not practical in a medium term. Anyway, the impact of Grover algorithm on hash function or symmetric cipher in general implies that more or less you have to increase the size of the output hash function or increase the size of your secret key. And for most symmetric cipher, actually this has been planned, this has been anticipated, that we have design for which they are flexible in terms of size and they can be scaled. So you don't need to change your hash function or primitive. You have just to take another size in the standard. So the impact on public key cryptography is more drastic, because we have the Shor algorithm, which will allow to factor in polynomial time the hard problems that we consider until now, which is factoring. And here I mentioned factoring, but actually the algorithm works exactly similarly for elliptic curves. So we have a polynomial time algorithm for breaking elliptic curves. So this means that the signature algorithms that are deployed today are completely insecure. And so we have to do something. But in fact, we are aware of this threat since a long time. So since 1994. And so the point is why we bother today about this issue. It is really relevant. And what changed, let's say in the next 15 years, is that the computational power of quantum computer increased a lot. And so an easy way to measure what is the power of a quantum computer is the number of qubits. So this is basically, it gives you insight on the size of the problems that you can handle. And so 10 years ago, you have quantum computer doing with only, let's say, 5 qubits. Recently, this increased a lot. And so the state of the art is that you have about 100 of qubits, and it has been demonstrated typically by Google that you can solve non-trivial problem with quantum computer, and you can start to assemble a large number of qubits. And just as a side remark, so the Nobel Prize that was awarded to this three researcher, in particular, their research lead to what is the quantum computer that Google using supraconducting qubit. And so it's related to their research on Nobel Prize. And actually, John Martinez was a senior scientist at Google when they do when they design the first generation of the Google quantum computer. And so if you want to track down, so what is this threat? It is real or not, how it will impact a blockchain or crypto in general. You can also follow the IBM roadmap that was released publicly a few years ago. And what is interesting is that until now, they follow all the milestones that they fixed. So this means that, let's say, in less than 10 years, you will have quantum computers which will basically we will be able to handle to break public key cryptography. At least this is what they wrote in the roadmap. And actually, it's not only large tech companies which are in this road to the biggest quantum computer. In Europe, for example, you have about 39 startups which are working on building a quantum computer. And why is this company are working, these 39 companies are working on building a quantum computer? Because actually there is not a unique way to design the basic unit of a quantum computer, which is a qubit. And you have several technologies. So I mentioned superconducting by Google, but in fact you can create qubits from other types of atoms, other type of technology like light and photonics. And you have several startups working in this area. And again, if you have a look on what are the targets in the next 10 years, you can start to see that it's starting to be quite important. And this kind of computer will be able to break cryptography typically. But there is a catch here on the number of qubits that are mentioned by startups company, because as of today, qubits are not perfect. So they are noisy. And you have to make a difference between what we call physical qubits, which are noisy, and logical qubits, which are the qubits which are perfect. And so we know from theoretical point of view is that 1,000 qubits are sufficient typically to break elliptic curves. So in fact, elliptic curves are easier to break than factoring, because the size of the object are smaller than factoring. So it's easier to break elliptic curves than to factor RSA, for example, with quantum algorithm. Indeed. And so qubits are noisy, and most of the unknowns that you will see, in fact, are related to physical qubits and not the actual logical qubits that we know that are necessary. And when you do the theoretical estimation for breaking on what is the size, what is the resource estimate that you need to break crypto. And a number that we need to have in mind is knowing that these qubits are perfect. So we know that more or less, typically for breaking elliptic curves, you will need about 100 of perfect qubits. Okay, and for factoring is 1,000 of qubits, perfect qubits. And as of today, since these qubits are not perfect, the number of actual qubits with the technologies that we have today is about 1 million. So there is a serious gap between what we have today and what will be needed to actually break elliptic curve. I would say hopefully, because to be frank, if tomorrow there is a quantum computer which is able to break cryptography, it will be quite terrible. And so that's why governments and security agency got very concerned about this issue, and they decided to say, okay, we have to update the cryptography, because we believe, so typically this is what the BSI, German security agency, say, that between 2040, we will be able to have a quantum computer to break. But this is still quite a long time to wait. And so why we started to worry and to update the standard, because there is one reason in general, and after I will discuss a bit more what is the impact more in the blockchain case. So the things on which we are more concerned is about encryption, at least, because we know that we can already today capture data, and wait for several years to have a large enough quantum computer capable of breaking this encryption. And so since you have data that needs to be kept secret for more than 10, 20, or even sometimes 100 years, there is already an issue. And most of the community until now focus on protecting confidentiality in the long term. Some work has been done also to assess the threat on a blockchain with respect to what I said from the beginning. So there is one thing which is related to the consensus mechanism. So here I mentioned a blockchain because I think this is the only scientific paper dedicated to blockchain is on Bitcoin, can be adapted for other type of blockchain, but the overall logic is the same. So you can use Grover algorithm maybe to speed up the consensus, and this could have an impact. So that's one issue. But the paper conclude, as I said at the beginning, that in the near term and middle term, this is not an issue because it's not so easy to implement in the next, at least since you have not too much memory. So the real concern is about the signature. And so for the signature, you have to assess whether how you can solve this issue, because typically it's known that you have a one-time address. So it's a global recommendation to not reuse the same address to spend your cryptocurrency. So this means that at least this aspect can be handled not at the technological level, but on the way that you manage the network. So once your transaction is on the blockchain, what you can do is to recover the public key, and from that to extract the secret key from the public key. But if we assume that this public key is used only once, that's okay. So in fact, the risk, and since there is no real threat on the hash function, once it is once the consensus mechanism is done and your transaction is on the blockchain, there is no issue on it. So the real issue is on the transaction that has been started but has not been processed completely. So this means the risk is to break more or less on the fly the signature schemes, and if you can do that, then you can steal cryptocurrency. So this also means that this puts some further practical limits on the attackant, because it's not like the encryption streets that you can wait forever and break your scheme. So you have a lot of time. So in this case, it depends of the blockchain that you consider, but you will have a time limit to break your schemes. So in the case of Bitcoin, it was estimated that you have to break the signature schemes with your quantum algorithm in less than 10 minutes. And this can depend on the blockchain. So that's still a serious issue because at the end, a blockchain is a trust machine. So it's something on which you have to trust right now and in the future. So I think this threat is sufficiently dangerous in general to consider what are the options to do that. And so one option, but I will not go too deep because the next talk is going to be about that, is to use a post-quantum crypto system. So the point is that what we are going to do is to replace the hardness assumptions that we have today by new one, typically lattice schemes that will be discussed after. So instead of having a group as a public key or an elliptic curve or a factor, you will have a public key, a matrix, and you will have a new hard problems related to that. And what is new as this year is that a standardization process, and so you have different problems that you have to consider for doing post-quantum and new hardness assumption. And so during several years, the community worked on that topic and decided what is the best algorithm that we have to consider. And in particular, we have now 3 signature algorithm, which has been standardized based on lattices, and another one which is purely based on the hardness of hash function. And so now we are starting to do the transition, the integration of all these standards at scale in application. And what are the challenges that you will have to solve for this algorithm? And in particular, in the case of signature algorithm, you can see from here that the objects that you have to consider, they are much bigger than what we used to have until now, and especially elliptic curve. So you multiply by 200 the size of your public key or the signature. In terms of computation, these schemes can be more or less equivalent to what you have today. So what is the first challenge when you do integration of post-quantum is the size, and especially in application for which efficiency is a serious issue. And so it will work for a lot of internet protocol, but for some particular application, it can be extremely challenging to handle all these tasks. And even more complicated than that. So we say, well, we have some new work problems that we believe are post-quantum, but as in the classical setting, we have no proof of that. So we believe it's true, so we evaluate with respect to the state of the art, but we still don't know. So we can have some surprise. And so the current recommendation worldwide is not to replace the classical algorithm directly by the post-quantum algorithm. The recommendation is to do both. And that will be even more challenging to do it. So actually, it's a European recommendation. The US recommendation is a bit different. So we are still in a time where we don't know what will be the position of everybody globally. But at least in Europe, there is a strong push to do hybrid integration. So not only post-quantum plus classical. And so, as I say, since they are bigger, this will be even more challenging. And so, one of the last points that I want to mention. So this is moving actually pretty fast because we know that within 10 years, typically, it will no longer be possible to communicate with the US using a non-post-quantum algorithm. So that's kind of a very strong statement. And we have basically the same type of recommendation at the EU level. And at least this transition is starting. As I said, in several applications, it will not be an issue. So this size constraint, typically right now, about 30% of the TLS traffic is already protected by a post-quantum algorithm, but just not the signature schemes. So they, at this stage, just implemented the protection for key exchange mechanism. And so in the next talk, you will see some actual implementation and challenges related to that. And to conclude, I just wanted to mention a few things that we are doing at EPITA. So I'm currently mounting a new share on the impact of quantum to cybersecurity in general. And the goal of this share is to gather academics and also industry to work on this topic of post-quantum transition, because there are issues at the intersection of practical deployment and also theory. And I believe that we need to gather a large community to work on that problem. So the research program is to work on most theoretical aspects, because it's still important to investigate whether we can improve from theoretical point of view these post-quantum schemes. Also, what are their security in the quantum setting? And also, we are working on the actual practical deployment of this technology, not yet in blockchain, maybe very soon on Ripple, but we did some implementation typically for DNSSEC, and we realized that indeed it can be very challenging for protocols which are efficient demanding to implement all these schemes. And this is not only a share related to research. We also include teaching, because we will develop also specific programs for EPITA students, specialized, but also in the engineering, in the global engineering curricula of EPITA. So that will be my conclusion. And just I mentioned here, so if you want to have some resources regarding post-quantum, you can go on this event that we organized last year, and there is a lot of YouTube videos and slides related to all the topics that I mentioned, but deeply in detail. Thank you.
Thank you. I was just wondering about like the Willow quantum computer. Does that require GPUs as well, or is that just completely different? Or can they work simultaneously or hybrid?
So as far as I know, the Willow quantum computer, there is no GPU involved. So it's a pure quantum processor. And so if you see on this picture, the quantum processor, actually the quantum part is only at the bottom of the thing. So it's a teeny things, and all these big things in gold, it's to make things working, to make it cool.
Part two, will you be able to create a hashing algorithm with that instead of GPUs going forward? Would this be like a new GPU that would be replicated and grown, like built upon the future?
Could you repeat the question?
Like the GPUs are right now are the compute, right, for hash algorithms, mining different things, right? Will this be the future version of that compute? Will these be multiplied and built, hash functions or other things like that?
So at least this is what in the papers that I mentioned, people try to evaluate. So indeed, to have a kind of new GPU for mining based on QPU, we call that. At this stage, I believe there is a long way for going in that direction. Probably in the next, what we could expect is the next 20 years, is a quantum computer sufficiently powerful enough, but quite, well, that you access in a cloud. I don't see yet a kind of deployment on like GPU on small piece like that.
Any other questions? Yeah.
So, is there a solution to protect the existing blockchains already, or do we have to scrap them in 10 years and just create the new ones?
Yeah, there is a way to protect them, but so there is two parts in your question. So, how to protect past transaction and how to protect future transaction. So, for the past, I think one good point that once it has been proceeded in the blockchain and due to this, it's okay. So there is nothing to do. And so what we have to think about is the new generation. And what you have to do is basically replace the elliptic curve algorithm by post-quantum. And in this replacement, so the question is, so you have three new signature algorithm. Which one is the best one? So that's one question. And second question is that is they are going to be efficient enough for the blockchain application? That's also a question. And third question is about hybrid, whether you do hybrid or not. So that's a recommendation as well. But yeah, so what is going to be the practical impact at the production level of this algorithm in the context of blockchain? I think that's a very interesting question.
Okay, let me chime in here. So it's not just a matter of you replace a signature with another algorithm. There are also properties of current signatures which are not so easy to replicate in this post-quantum. For example, you want to do threshold signature for custodians, you want to use aggregation signature for speed up. All these more evolved signature properties, they're not yet understood for post-quantum, so it's not so easy.
Yeah, plus one. So I kind of mentioned kind of the most direct, obvious impact, but there is a lot of, so blockchain and it's great. We have a lot of very advanced crypto primitive that we use with incredible properties from Diffie-Hellman and so on. And all of that not disappear, but well, much more complicated to achieve in the post-quantum setting. So typically, yes, I'm working in threshold signature in the post-quantum setting as well.
Thank you. Thank you very much, Professor Perret. Hope to see you again soon at the XRPL.